Now let's go and look at it. So I will go load this in, and some of you should have received it. No. Okay, so example models, and there's a thing called ABM model with birth death. Okay. Okay. So we're gonna open it. Okay. Yes, close it. Okay. I'm just loading it in. Good. Okay. So first of all, let's go run this model. What you'll see in this model is some features that illustrate how certain things could be done in any logic. So here's a model. It's nothing too fancy. It's actually not that pretty, that's for sure. But here we have individuals who are scattered within a population. The individuals are colored according to their infection status, susceptible, infective. They are further encoded as to their age by their sort of the width of the appropriate circle. They're connected in networks, and there's actually grouping together of people within families. So you can have, for example, when a baby's born, it's located near a mother, and over time they grow. So we see here over time people coming into the model. This is going a little bit fast here, so I'm gonna just show it this way. So you see people coming into the population through two processes: immigration and through births over time. And you see there's certain connections which are highlighted in red, and I believe that those connections were associated. They have special semantics. I think it may be a connection between mother and child, something along those lines, but I'd have to go back and check. I further have some statistics sort of computed down here at the bottom of the model. But a lot of the interesting dynamics are actually occurring at the individual level. So if we go down to this, we could see that we have a population of I think it's 3,600 or so. So each individual, I noted that they're served with susceptible infected. Why do we see this thing here? What is this used for again? Can anyone remind me? It's a branch, yeah. And it's a branch from, what's this thing? Yeah, the entrance. So when they first come in, they're put each in this category, that category. Note that their current category is indicated here with this highlighting. And you'll notice there's several categories here. So there's pregnancy and sort of infection status. You'll notice that the sex and ethnicity are sort of specified here for these individuals. And you'll notice that it actually uses descriptions here that are meaningful English descriptions, not just 0 or 1, for example. How do we accomplish that? Anyone want to guess? Enums. That was a fine guess, Kurt. So if we go to person, for example, we'll go and within person, we can go to, I think it's in the exact tab. I'm having trouble remembering if it's in advanced or if it's in yes, here it is, advanced. You'll notice there's a declaration of an enum for sex, and it specifies you're either male or female. Similarly for ethnicity, there's a set of possible ethnicities. So here we have the capacity to indicate someone's sex, not just numerically, but using these familiar identifiers. Among other things, that means that when we specify a person's sex using a parameter here, sex, the actual class. The actual type associated with that sex is in fact the enum sex, or personhood sex. The distinction of sex as defined in person. This is the sort of Java syntax, because this thing is defined in person. It's defined associated with that person. So here we have people distinguished as to their sex in that sort of way. Similarly, their ethnicity is defined as being associated with this so-called enum, this enumerated value ethnicity, which we just saw defined there as well. So that's kind of an interesting feature of this model. Let's go back to the display. I'll highlight some additional features of the model. Another thing that's kind of interesting is that here we keep track of people's children over time, as well as for their mother, for example, the person who's their mother with the population. So a mother here keeps track of her children. So this is person 0 in the population, but she has this other person, 1412, as a child. This is what's called a collection in any logic, and it is sorted through the interface here. Up here through this so-called collection interface. So if we were to go look, for example, at person here, we can go see that a collection is associated with it's associated with a certain type of data structure which stores this information, namely an array list of person. Okay, so it's keeps track of sort of a vector, a sequence of persons in the order that they were added. And there's actually a process by which individuals give birth in this model. So there's actually you can see the set of functions, and some of these functions have to do with this whole children. So for example, here's the thing which adds in a baby to the children associated with the mother. Okay, so this is what adds a baby in when it's born here. When do you think that birth occurs? When would that birth happen here? Anyone?
In the pregnant state?
Yeah, when you go from the pregnant state to the non-pregnant state, and that delivery occurs. How long? It's sort of. How do you think that schedule? Is that a rate transition? Well, in this case, I've represented as a timeout as 0.75 years or 9 months. In general, suppose you wanted. So let me ask this. Riddle me this. Suppose I wanted to capture variability. So suppose you look at this and you say, well, that's good. I mean, you have an average of 9 months, but in fact, it's variable. Some babies are born early. There's preemies. There's babies born late. So you have variability. Suppose you wanted to capture variability. Suppose someone came to you and said, well, one way you could capture variability is just have a rate transition. Just have a rate here with a average time, a rate constant of what? What would the rate constant be if we did this? 1 over 0.75 would mean that we have an average time in this state of 0.75, right? Now, would that be a good way to capture variability? Why? When's the most likely time the woman would give birth then? What does the probability distribution look like? If I made it a rate, I've drawn this curve many times now in this class. If it's a rate, it's a certain chance per unit time of leaving, right? So there's a probability of remaining in this state over time, remaining pregnant, right? What does that look like? What's the chance of remaining pregnant after time t look like? It's an exponential decrease. Remember, it's e to the minus lambda t. Where's this lambda from? Oh, sorry, lambda. Alpha, sorry. Where's the alpha from? Yeah, it's the rate constant. And it would be in this case, it would be 1 over 0.75 if we want to have an average, ladies and gentlemen, of 0.75, some average time of 0.75. The rate constant, this guy here would need to be alpha equals 1 over 0.75, right? So we could have that. Is that a good way to represent this? No, because what's the chance per unit time? So conditional on you being in this state, still being in this state. This is your chance of still being in the state. What's the chance of being born within the next little bit of time? Well, it's alpha times dt, or alpha times delta t, if you want to think of it. It's this next little bit of time. It's 0.01 of a year. Over that much, I have alpha times that chance of being born, where alpha is this guy here. And ladies and gentlemen, if we graph out therefore the chance that you will transition within a given period of time, it's shaped exactly like this. It's just alpha times this. Right? So because it's alpha times this probability of sort of chance of leaving in here. So we're going to have this just scaled by a constant. So what it's saying is the people are more likely to leave early than late. So this is not a particularly good way of capturing that. Suppose we want to capture the variation. How could you do it?
You put a function in the timeout.
Okay, good. So ladies and gentlemen, I want to pay attention to what Kurt just said. Put a function in the timeout. Don't get trapped, ladies and gentlemen. Don't get trapped within the notion that a timeout has to be a fixed thing. You could have a timeout that itself is a draw from a distribution, a probability distribution. What could that probability distribution look like? Well, it could look like any probability distribution you want. If you have a distribution associated with when babies are born, you could plug that in and look it up in that distribution. And you could draw from that distribution. That's great. So I could draw that. What does that really mean? If I drew from a distribution here, if I were to draw from a normal distribution, something like that, if I were to draw from a normal with a mean 0.75, oh gosh, got to be careful here. I think it's the opposite order. Yeah, look at this. It is sigma first. Gosh. So if I were to approximate this by a normal distribution, something like that, I'd probably want a minimum of 0. Well, minimum that's truncated. In any case, if I were to do this, what would that mean? Does that mean that when the model starts up, it's going to determine this? It's going to pick a value, and then from now on, everyone's going to leave in exactly that amount of time? Every time someone comes into here, that's when it schedules when they're going to leave, actually. It sort of schedules, oh, you're going to leave that. So here, it'll just draw. Every time someone comes in, it'll draw from this distribution, which is what we want. Suppose we wanted a custom distribution. Suppose we wanted a distribution that was purely custom. Well, we can actually do it. We can use it through a combination of two things, ladies and gentlemen. This is like a tour of things that you might not have otherwise known about. Maybe that's not a bad thing. So we could have a table function, which is, a table function that specifies probability over time associated with being born within a certain interval. And this might be specified in terms of years, so we might have, up to half of term. There's basically no chance of being born then, and then above then there's a certain chance of being born in each successive interval. And I'm not going to go fill it in right now, but the basic point is that we could specify successive sort of probability, so-called density, some chance per per small amount of time that need to be born within that period. And by specifying this, we can actually create a custom distribution based on this. So we can sort of draw out a custom distribution that we want to use for our system. So maybe we have some distribution from empirical data, and we can create a so-called custom distribution object that would capture that distribution for us. And then what we could do is we could call that custom distribution, for example, in the timing of this state here. Okay, so that it turns out would be quite straightforward. In fact, if I wanted to do that, maybe I will just put a variable in here. So variable would be something like custom pregnancy duration distribution, something like that. And this would be something called a custom, and I think it's called a custom distribution. I won't push this if I've forgotten it, but my recollection is that it's a custom distribution. Okay, no, it's there we go, custom distribution, yeah. And then we can pass it a value, for example, associated with new custom distribution. Let's go, oops, custom distribution, there we go. And then we can pass it new custom distribution, passing it this table function. And this table function might be, empirical table function, empirical pregnancy duration, empirical pregnancy duration PDF. That's a probability distribution density function. And then we have this custom distribution, which would depend upon exactly that that table function. So let's go up there and go do that. Okay. So we can actually pass it. I'm pretty sure the custom distribution takes. Okay. So yeah, what does it take as an argument? Okay. Yes. What does it accept? No. Okay. I'd have to look up to be absolutely sure, but I'm pretty sure that it takes this as an argument. So here we can use these sort of table functions to specify distributions of interest, and then what we would do is we could specify. Yep, it built successfully, and so then we can specify here that we want to draw from this custom pregnancy duration distribution, and we want to do a get from it. So returns a random variable distributed according to the given table of pairs. So there we can draw from this distribution. Okay, so here the key point is that a timeout doesn't necessarily mean a fixed time. Let's put it this way: it doesn't mean the same time always. You could draw from a distribution, and this is a way to have an arbitrary distribution associated with timings, or associated with the timings by which you go from one state to the other. After this amount of time, it will go up there, and it can draw that from a distribution. Okay, does that make sense?
Specify any specific distribution?
Well, we could. I mean, an alternative to that, this would be if you had empirical data. Like if you had data and you wanted to do it non-parametrically, you wanted to just use that data as sort of the best data. Another possibility is you could, as I said earlier, you could do a normal distribution, or a log normal, or you could do a beta distribution. If you have some specific distributional assumptions that you can bring to bear, great. You could use them, and that's fine. It's just you're not limited to that. Okay, so we can do it with a specified parametrically specified distribution, one that it has a known form, beta or log normal or gamma or Gompertz or uniform or triangle or what have you. There's all these distributions you can draw on if you know their parameters. But if you don't know their parameters and you have empirical data, and it's not a particularly good fit to one of those distributions, you could just use that empirical data directly. Does that make sense? Yeah. Okay. So that's a sort of a feature of the model. Let's talk about some other things. You'll notice here that we have some additional elements associated with age. So you'll notice, for example, here, people's age is given, and there's actually a function called current age. Okay, and if I were to run this model up here, and I were to click on an individual, I have it reporting on a lot of information about that individual. This reports, I think, their children, is my recollection, but I could actually report their current age. And in fact, if we go up to their representation, their so-called presentation, what we'll find is that their width, is actually dependent on their age. In other words, the radius associated with their circle depends on their age. So actually, it's called circle size and circle size. Sort of bucked Java convention by naming these things in uppercase, but you'll notice that it calls to current age. What's notable here is let's set it so that when we click on them, we can report their current age in terms of the results. So here we go, and maybe I'll say, trace ln is, and I'll call this current age years old. Okay, so I'm going to report how old this person is. Now, in order to do that, to get it, I'm going to have to rebuild it so that in other words, recompile it so that it knows about the changes. Okay, so here, oh, look at that. Oh, gosh. Well, no random generator was set. Okay, that's, okay, use get random. Okay, I need to set the random number generator. Well, that's, yeah, it looks like you have to associate with the custom distribution a random number generator, which is fine. This shouldn't, I may deal with that in a bit, but you notice when I click on this person, it actually reports the age. And what's notable is that's a continuous age. I want you to reflect on that. Within our system dynamics model, how do we capture age? How do we capture a population that has different ages? A stock. Okay, so we do so with stocks. That's how we capture the memory of the population, sort of the current situation of the population with the stock. So fair enough. Suppose we want to distinguish people by their age. What would we have to do? Different stocks for different age groups. So we might have stocks for people who are children, people who are sort of medium, reproductive age adults, and then people who are elderly, right? Or we might have 5-year age categories or 1-year age categories. We can do that. Can we, ladies and gentlemen, in the system dynamics model, specify an arbitrarily fine distribution of people by age? Yeah. No. We're not going to be able to have sort of real value at ages. You can break it down as finely as you want, but it's always going to be discrete categories. 0 to 1 month, 1 month to 2 months. I mean, you can break it down further and further, but it's going to be discrete categories, and you can be flowing between those. Here, we can actually have continuous age. I want to show you how that's accomplished, ladies and gentlemen. So let's go look at this. So the basic mechanisms are actually shown here: appearance time, initial age, and current age. So how does that work? Let's go see what this current age does. So here's current age. It'll be actually yet simpler if everyone were born into the model rather than being there initially. So current age specifies, okay, maybe they have some initial age, and then we take, what do you think this thing does? What do you think appearance time is? Or if they were born, or when they came about in the model, maybe through immigration, or maybe through being there at the initial state of the model. They were initially there, so they have some appearance time at time 0, right? Time, what do you think that is? That's the current time. So here they have some initial age, the time that the age that they were when they first appeared. Maybe they were in the model at the initial state. They were 37.382 years old at the initial state of the model. Then maybe the current time is 5, and they were there from the start, so this is 0. So we just add 5 years to that, to their initial time. On the other hand, maybe they were born into their model. What's the initial age then? 0. You take the current time minus the time they were born in that case, and you get their current age too. So here we have people aging in a continuous fashion. Now, why is that interesting or important? Why not just have people age in a way that's into a set of categories? Why does having continuous age sometimes help? You can have arbitrary categories. You can have categories that are not uniform, different categories for dividing up the population for different statistics. So maybe you're trying to compare the model's results against some statistics which are broken down into 5-year age categories, some into 2-year age categories. You don't have to do the sort of the least common denominator, do it in 1-year age categories, you can capture both. You have it as finely as possible, but you could summarize in any number of different ways. Another example is that sometimes in certain age categories, like for very earliest years of life, you break it down really finely, and then older ages, you break it down more coarsely or something. And this allows for very readily accommodating different specificities, different levels of precision of age. And allows you to very flexibly sort of summarize it as you see fit. In short, ladies and gentlemen, it decouples the structure of the model, how you happen to divide the population up, for example, from the vagaries of the reporting, whether you want to report it to 2 years or by 1 year or 5-year age categories. At a conceptual level, we talk in software engineering about a separation of concerns. You separate into different pieces of a program or a model things that deal with different types of issues. And something that deals with different types of issues is, for example, the reporting on model results versus kind of the mechanisms, how we accomplish that. And with a system dynamics model, when you're stratifying, to some degree your decisions on how you break up the population, the structure of the model is dictated by your reporting considerations. What are the breakdowns you want to use for your reporting? What are the breakdowns you want to use for matching up model results? Here we have a decoupling of them. We can store it as fine-grained as possible, and really this is essentially no cost. And we don't even have to increase the age here, right? There's nothing here, there's no moving part associated with age that says time to move their age up, right? Where is that? Do you see it? No, you don't see it because it ain't there. There's nothing here. There's no sort of process that says, it's the first of the month. It's time to increase everyone's age by 1 month or something. Do you see that? There's nothing. This is all there is. It's just this calculation. You say, what is your age? And it says, oh, when was I born? Well, it says, when did I appear? And what was the time that I appeared? And how old was I when I appeared? And what's the current time? Boom, done. calculation, right? No moving parts. No moving parts. You can double the population size. It doesn't take any more time to kind of do this sort of calculation. So that's kind of nice, and it does allow for that flexibility of reporting. Does that make sense to people? Why that's advantageous? It's kind of a nice thing. Now, do I do this for all models? No, because sometimes I just find it easier visually or what have you to do it, break it down into fixed age categories with fixed timeouts. That's also fine, but this is a very flexible pattern that you can use when you want to. Okay, so let's see what other things. Well, okay, there are some extra things here that are kind of interesting. One is here I have some components that this is what's called a hash table. Some of you may know what that is. It's sort of something that maps from keys to values. And what I'm doing here is I have a situation where I can record over time sort of someone's history, for example, of being infected. So there's this sort of dictionary: last time infected for person, last time exposed for person, etc. So when someone's infected, I can store it away in this dictionary, and basically that allows me to give sort of a description of someone's history of infection over time. I don't actually know if that's stored. One thing I'll show you is, so it's last time infected, and if I search here, any logic search mechanism will allow you to will allow you to sort of show the different pieces of it. I can do it in the entire workspace. Okay, here we go. So you'll notice it's called here, but it looks like it's not actually being used currently. To have it be used currently, I could have it right here. I could, for example, store, so when someone's infected here, in this action, I could have, oh, you know where it is? Oh, that's where it is, I think. Excuse me, no, I would have found it there. Well, maybe not, actually. I think, okay, so here, so ladies and gentlemen, what happens when a person gets a message? Okay, but they get a message. Where does that message get passed to? That's where it is. That's where it is. Where does that message get passed to? So when they get a message, how does it know what state chart to go to? Ladies and gentlemen, the answer in this case is not blowing in the wind. Instead, the answer is right in front of your eyes. And it's not me. It's this. It's this. You could say forward message to, okay? And what this is basically saying is, for messages to come in, where do I put them? Okay, this message comes in. To which state chart do I give it, if any? And we can either do this forward message to. This was in the video, I think, about messages. We can either say, okay, route it to one or the other, or we can do it manually. Here it's doing it manually. So you notice it says on message received. What I'm going to do is I'm going to save away their history information. I'm going to save away what the message was and who the sender is. Where did that information come from? Help me parse this. Where does this sender come from? How would I find out information on it? Ladies and gentlemen, the answer is not blowing in the wind. It's sitting in front of you, and it's not me. Where is it? Where would I go to ask? Okay, where would I go to find out where the sender is defined?
Oh, in the beginning of the table?
Yeah, you'll notice it's over here. See this? Remember, I think I mentioned before to you. I think I did that you have these little indications here that provide what sort of contextual information is. Do you remember we saw that before for index? Remember that whole thing with we had the replicated line and we had what's dx and dy. We started typing and there was this little light bulb there, and then it says it says use message. So it's saying, okay, hey, I'm providing you with this contextual information. MSG refers to the received message, and sender refers to the message sender. So in this context, I can refer to these things and make use of them. What I'm doing here is I'm saving away this information for later reflection. So when I have this message, then or when I want to inspect on this person, I could report all of the times that they're infected, for example. I can report all the cases, the timing, and who infected them or who exposed them to infection associated with this MSG, okay? And then I pass on this thing, the message, to the appropriate state chart, in which case this is the infection state chart. There's no interaction with the pregnancy state chart. Ladies and gentlemen, this is a very important point. Please don't miss this one. If you have multiple state charts and you have multiple message types, maybe you have a hepatitis C infection message, and maybe you have a HIV infection message, maybe you have a flu infection message. If you get a flu infection message, you want to send that to the flu state chart often. If you have an HIV infection message, you want to send an HIV state chart, Hep C message, Hep C state chart. So right up here, you could say, what sort of message is this, and route it to the appropriate state chart, just like someone in the post office sorting mail in the days of old. Yes, Kurt?
Don't you have, when you're on a message received, aren't you able to specify what the message says?
Yes.
So that you don't need any of this functionality, because anytime you get a message, then all the state charts that are potentially able to receive the message, they receive the message, but then only the one that says infect flu can go through.
Correct.
The other ones are messages
Correct.
that says infect something else.
Okay, so this is a good question. So may I unpack your question? Okay, so with your pardon, I'll answer it now rather than nuggetizing. So the question, as I understand it, from our member in the back, is had to do with the fact that, wait a minute, why do we have to route messages between different state charts? Why would we, for example, here say, what sort of message is it? Send it to state chart X if it's relevant to state chart X, state chart Y if it's relevant to state chart Y. Why don't we just let them all shake it out by within the state charts? They know what they're listening for.
Right.
So, for example, here, let's go look here. Ladies and gentlemen, here before us lies a transition from susceptible to infected. What sort of transition is that? Okay. That's true. It's in fact a message one, and although my machine may keep you in suspense, you notice it is a message one. In fact, it says to fire unconditionally. In this case, so it's a message transition. So it's going to fire when a message comes in. It says message type is other. Okay, fine. And it fires unconditionally. It doesn't check the message contents. So one way would be to have each of the state charts just fire unconditionally for the right sort of message. You know, if a message comes to it, you fire. Okay, it knows whatever message comes to me is one that's relevant to this, so it just fires. In which case you could route them accordingly and just send the appropriate one to the appropriate state chart. And with confidence, it could handle it, knowing the only message that could be is the message for me. Alternatively, as Kurt has suggested, you could do this if message equals, right? And you could say, for example, if message equals such and such, then do something. Now, this sample message is actually something that's present to myself from probably 2 years ago. Commonly, what do we have in here? If message, the common reflex is to put in if message equals like HIV infection, right? Or hepatitis C infection, or put in flu infection. What's the problem with doing that? Could we do that? Yes or no? Yes, and what would we need to do when we send a message?
Well, first of all, the message has to be type string, right?
Yeah, it would have to be of type string, yes. And you would send a message like this, right?
Yeah.
With appropriate day, it would say like flu infection, right? So if we were to do that, if we were to make it so that it's of type string and we were to have it depend on this, so it looks something like this, would that work? It would. It would. It would work. What's the downside of this? Put on your hat as software engineers, ladies and gentlemen. I know it's an unfamiliar hat to many of you. Perhaps it's one that bites a bit too harshly into the scalp. But what's the problem? No, the problem is that you may mistype things. Here I type influenza, there I type flu. When I send it, I type flu, here I type influenza. When I may put a capital F in some cases, in other cases do lower F. There's no enforcement. There's no enforcement of regularity. In other words, it's not checking that this is a consistent message with where it's sent. And that's dangerous, ladies and gentlemen, because it can lead to a bug. It could be as simple as something like having capital F here and lowercase f. Treats it as a different message. Do those things occur? They occur in spades.
I do know it.
Yes, they occur a great deal. So it's actually better to use a what? To use an enum. Where do we see the enum before? Can anyone remember? So we saw it when we had here under person, we had introduced those enums for ethnicity and gender. It's under, I think, advanced in person. Here we go. And so I could have a, enum public, enum, messages, and this could be, HIV infection message or something like that, and Hep C infection message, and influenza infection message. Why would I do that? That may seem sort of egregious, but why do I do that? There's only 3 possible messages, and so I don't just gratuitously mistype it. In other words, ladies and gentlemen, so then there'd be some consistency in place. So if this was an influenza, so I'd actually have to do message, I think it'd actually be person dot message, actually don't need the person, this good, dot messages dot influenza infection message, and then when they are exposing someone here, I could send an influenza infection message, and it's because there's only those 3 types here, it's going to make sure that they're sent the same. And I should have been careful with this. Back to this guy, I'm going to make sure that the message that's received here is of the appropriate type. In this case, what is the type? Well, it's actually a person dot messages. That's the sort of the type of it. Okay, so that should work. Okay, so Bill completed successfully, so that's good. So here we have this sort of situation with messages, and you're right that we could route all messages to all state charts, and they only electively handle those that are germane to them, that would be acceptable. It's a little bit more work because you're delivering to more places, but the performance costs would be extremely modest, so I wouldn't be too concerned about it. My bigger concern would just be how clean, whether it's clean, and I think it would be reasonably clean. So this is an example model. Any questions on this model? Question? Yes.
In the person thing, you had the destroy code.
Yeah, I had destroy code in person. Yeah.
Does the destroy code happen when they go into a final state, or does it happen when you call some destroy function on the system?
The destroy code occurs when they disappear. And look, can I show you how? That's my recollection. And so when they're removed from the population, you'll notice here that if they go into a death state, they can actually get removed from the population. I think actually this death occurs. See, there's a thing called finalized death, and finalized death will end up reporting some information on them, and then it removes them from the population. So to be sort of clear, this get main remove population. So in other words, they're removed from the population, and when they're removed from the population, it's at that point I think that destroy code gets invoked. Okay, when they're going to be disappearing actually. It's not when they go into this state here, which let's put it this way: if in this case the transition's going to the state, actually tell it finalize death. But if you had a transition which didn't force that, they could go into that state and just sit there. Yeah. Okay. Any other questions? Questions? Questions on any logic? Nothing? Oh man. Silence. I think we're going to do something radically different this next time to deal with the silence. And I think I'm going to give you an assignment to do in class with me. And I'm going to go round and do my rounds. People can pair up. I'll be great. I'm going to go around and I'm going to look over your shoulder and help you. What do you think? Okay. Maybe I shouldn't have told you, so you come and be surprised.
Oh, I mean, next week we're going to have an ice cream party.
So, well, you could have an ice cream model if you want, but we could have the model of an ice cream party in the simulation. Okay, so I think I'm going to do that. I think I'm going to have us build a model next time, and we'll get as far as we can, and then you'll finish it separately. Good or not? Okay. Okay. Thank you, folks. And one of the teams wants to meet now, so we'll meet now.